Okay, so we're going to be finishing up section 3 today. So if you recall from I'm having 3.4 thing. There's some issues with the yep. Just sorry. Okay, so there's some issues at the bottom of TGO 3.15. If you did not complete that or had an issue, you can just put that at the beginning of next homework assignment. There we go. All right, so we're going to kind of have this concept now where we're going to talk about stage delay, particularly the concept of logical effort. So as you recall, we kind of derived with CMOS and NMOS that the combined logical effort is going to be 1, and the reason why is because we define logical effort as the ratio of the input capacitance of the particular logic circuit to the ratio of the logic to the inverter. So the logical effort is just 3 divided by 3, which is 1. So this is example 3.7. That's going to be the stage delay of a fan out of 4 inverter. You see FO4, fan out of 4, so you have an inverter, and it is driving 4 inverters. So the electrical effort is just 1 plus 1 plus 1 plus 1 divided by 1. So that's fan out of 4, so that's kind of how the electrical effort makes sense. And again, we define our parasitic delay of an inverter as 1. So now we just take our equations here. We have the delay is equal to our gate delay, our electrical effort, and parasitic delay. So our parasitic delay is defined as 1. And then we add G times H, which is just logical effort times electrical effort. So this becomes 4 times 1, so it becomes 1 plus 4, and 5. So our stage delay is just the delay of the inverter, plus we have to consider what it's driving further on in the circuit. Because it's not just that we have the input, right? We have to worry about the amount of the time it's going to take to rise to be able to power, to be able to put the appropriate voltage onto the PMOS and NMOS circuits of all 4 of those inverters. So we have a poly, kind of combining concepts now. So we have poly driving the poly input to each of these inverters, and then you have to have your PMOS and NMOS circuits. You have to be able to create the channel for the appropriate, depending on the supply voltage and ground to each inverter. And then in order to do that, you have to be able to supply that voltage to each and every one to be able to create the current. So that's why you can worry about this concept of stage delay. Okay, so now we're going to deal with this concept of what's known as a ring oscillator. So this is example 3.8. A ring oscillator, you just have an odd number of inverters. So you start out, you have your normal signal, 0, you invert it to 1. Next one you go to 0. Next one you go to 1. So if you have an odd number, what's going to happen is if you do this feedback here, it's just going to oscillate. And this is very useful if you're trying to drive a clock. So you get some sort of delay signal, you tie it to VDD and ground. You start the input, you ensure power is maintained, and then that output is going to drive some circuit. So we want to figure out, we want to estimate the frequency of this end-stage ring oscillator. And this is important. There's another reason this is important is because if you have some sort of input frequency, right, and you're trying to divide it or lengthen it out, you can use these types of circuits in order to manipulate the actual input frequency. So initially, we know that the logical effort of the inverter is 1, 3 over 3, like before. Additionally, the electrical effort of the inverter is 1. Here, we have 4 inverters in the previous problem, so we have to add 4 and divide it by 1. Here, it's just driving 1 inverter. Each inverter is driving the next inverter. So therefore, we just take delay, parasitic delay we define as 1. G times H is just 1 times 1. The electrical effort and the logical effort. And this becomes 2. So therefore, each stage delay is going to be 2. So now, this means that we have for n stages is 2 times n. So here's the other trick about inverters. In order to get the entire frequency, and this is where the wording of the problem is important, estimate the frequency. The stage delay has to happen twice. And the reason why is you get your initial input, it changes to 1, and it changes to 0. The frequency is the time it takes to get back to the initial value, right? So therefore, you have to multiply it by 2. So here, we have the stage delay is 2. We know it's n stage ring oscillator, so it becomes 2n. We multiply it by 2, so it becomes 4n. And then the frequency is just 1 over the period. So now we have 4n, 1 over 4n. So if we want the frequency to be 1 over 20, we just have a 5-stage ring oscillator. Does that make sense? Well, then I'm going to go past 3.7 now. Okay, so now what we're going to be doing is we're going to be, I think I get this last part here. So up to this point, we've been talking about we have an inverter, it drives all of the other inverters. We had the previous example where we had a 3-input NAND gate driving n 3-input NAND gates, right? And we don't have anything, we haven't really considered any other instances where we have inputs from other circuits, or we're trying to calculate one specific path because here's our output that we care about for this particular calculation, and we have all these other things that we need to worry about. So now we're going to be worrying about logical efforts on specific paths. Particularly, you can think about critical path. Critical path, if you're trying to reduce the delay of the critical path, that means you're reducing the delay of the overall circuit. If you recall from example 3.1, we figured out the critical path delay, and then in order for both of them to come out at the same time, we had to add a buffer to that output. If you minimize the logical effort, you minimize the stage delay of the critical path, then if you're trying to ensure the timing is proper, you can reduce the amount of buffering that you have to do on the other paths. If you reduce the amount of buffering you have to do, that means you're reducing area. That means you're reducing power consumption. So this is where, trying to deal with these kind of issues it will benefit you. Additionally, calculating logical effort paths will help you in designing circuits. One of the biggest problems is previous CMOS courses, like Kevin alluded to earlier, where people are working on these projects for hours and hours and hours and hours. They'll do this concept called simulating and tweaking. Work on it, they'll design a circuit, and it doesn't work quite right, so they'll try to tweak the areas. You might move the polys, move this all around. Doesn't work. Move it around, doesn't work. You can save yourself a ton of time and energy by calculating logical effort of paths. So this is why I included this statement here. Logical effort provides a simple method to choose the best topology and number of stages of logic for a function. And we're going to be going over an example later today where I have 4 different designs of a 6-input AND gate. And you can calculate the specific logical effort for each of those based on stage delays and which one is best to drive specific circuits. So if you are using it to drive a bus, if you may have a 32-bit bus or a 32-bit data path, you have 16 bits, 8 bits. If you're trying to figure out how many lines you're trying to drive, there are specific designs that are better for each one. Okay? So we're going to be using this logical effort of paths to be able to determine the best design, because you'll be able to see that just using a 6-input AND gate, that isn't necessarily, sufficient. You can use just specific cell to be able to optimize your design. So here we are going to define the pathological effort as expression of the products of the logical effort of each stage along the path. So G is just the product of each logical effort on that path. And for those of you who don't recognize the symbol, it's similar. We have summation of G of I, right, is equal to G of 1 plus G of 2 plus G of 3. Here, this is just multiplying. For those of you whose math recollection is a little off, especially if your brain got thawed in the sleep, ice or whatever. And so we also, since we knew logical effort and electrical effort previously, we also want to deal with pathological effort and path electrical effort. So we find pathological effort is G, and uppercase G and uppercase H. Now remember from the previous we had the delay is equal to the parasitic delay plus the multiple of the logical effort and the path effort. And we're going to show that here we have some multiples here. For the next one. So the pathological effort H, uppercase H, can be given as the ratio of the output capacitance the path must drive. So going back to this simple example earlier, we have to have an output capacitance to be able to drive all of these circuits, divided by the input capacitance presented by the path. So when we get down to this example 3.9, we're going to see that we're going to go forward in calculating delay, and then we're going to work backwards through the circuit and calculate this effort. Well, wake up. There you go. And so the path effort is the product of the stage efforts of each stage. So it's, recall, we had G and H for this path effort, right? So this effort, and then we had our parasitic delay is equal to the stage delay. So now we are going to have this multiple of G of each G and H, right? So we have our logical effort and our electrical effort. We multiply those together for each stage, and then we're going to be multiplying all of those to get this path effort. And so this is a simple example 3.9. We're going to be using this to determine the pathological effort. So we're going to take these definitions and see it in an example. So we have an inverter. We have a NOR gate. We have a NAND gate and another inverter, and we have an output capacitance of 20. Right? So here's how this works. We know that the logical effort of an inverter is 1, and we're going to define our path effort as 20 over Z. So we have some sort of effort, we have our input and output capacitance, right? And we don't know. But here's the thing about this, because they multiply, they're going to cancel out. So we're going to have 20 over, does everybody have the path effort definition? Okay. So I can scroll up here. So here's the thing. They're going to start canceling out. We're going to have 20 over Z times Z over Y times Y over X times X over 10. For our pathological effort. So even though we don't know the intermediate capacitances that have to be driven, it doesn't matter because it becomes a ratio of the input and output. So the pathological effort, we start at 1. We know that The NOR gate is 4 over 3, the 2 input NOR gate. We've defined that previously. We also know that NAND is 5. NOR is 5 over 3, NAND is 4 over 3, and the 2 inverters are 1 and 1, right? So the pathological effort just becomes the multiple of all of those. So we have 1, 4 over 3, 5 over 3, and 1. Multiply those out, this becomes 20 over 6. So that becomes our pathological effort. So what you do, just scroll up for a second. Kevin, this is where you press pause. You go back to this table, right? So remember, NAND and NOR, 4 over 3, 5 over 3, and 1. So that's where our logical efforts come into play. So multiply all those out using the definitions for path effort. And then the pathological effort, so we have some capacitance has to be driven Z. And remember, using this definition, output over input, Z over Y. So this becomes 20 over Z times C over Y times Y over X times X over 10. So then what ends up happening is you get 20 over Z times Z over Y times Y over X times X over 10, right? So then these just start canceling out. So this just becomes 20 over 10, which is 2. Now before, I've kind of alluded to this already, but since we're accounting for fan out and multiple paths, we had this previous equation where E, the delay is equal to parasitic delay plus G of H, right? So now we've calculated this path logical effort, path logical effort, and path effort, right? So we have G of H. But what we're going to do here next is we're going to prove that you can't just do that. And the reason why is you have to worry about multiple paths in the circuit. So this is where it becomes a little more complicated. Yes? 20 over 9. 20 over 9, yes. 20 over 9. 4 thirds, 5 thirds, it becomes 20 over 9, yes. Let you correct that in your notes. So what happens, you type everything up, okay, you get the occasional mistake. Happens to the best of us. He said it. Well, I mean, if you good life lesson is that you can, it's good to, there's no shame in admitting mistakes, especially if they're minor, like that. I mean, the worst thing you can do is when you've made a mistake is just go, no, I haven't, which I have a particular professor back at USF in mind. He knows what I'm talking about. All right, so, no, okay, so now we have this instance where we have an inverter, and we have 2 inverters that it's driving, and we have our output capacitances, right? So again, with our path effort, we just know that it's 90 over 15 is 15 over 5. This 15 are cancel out, and it's just going to become 90 over 5, right? We also know that our logical effort is 1 for each one, right? So why are these cancel out? Just because of the definition, where it's going to be the output over the input. So we have 90 over 15. Right. Yeah. 15 over 5. So then becomes 18 times 1, right? Here. So here's the thing to recall. For our output path, we have to worry about the output 15 plus 15, right? Where in our previous problem when we were working on the fan out of 4 inverter, we had each effort, each capacitance that we would worry about because it fans out. So this becomes 15 plus 15, this becomes 30 over 5, which is 6. And we know that this path, again, 90 over 15, here's 6. And then we know that F, if we're multiple here, so this becomes 6 times 6, 36, which is 2 times our previously calculated value here. So now we've just proven that we can't just claim that F equals G plus H because we have to worry about multiple paths. So we have this concept of logical effort. We have electrical effort. So now we're going to introduce another concept called branching effort. Yes.
So why was it not? I know it's because of the CL cathode.
Right, because the definition. Let's revisit this definition, because this going through the definition again will help. The pathological effort can be given as the ratio of the output capacitance the path must drive divided by the input capacitance presented by the path. Right? So we go back to this example here. We have the input capacitance presented by the path is 5. The capacitance that the path must drive by the definition, we have 90 over 15 times 15 over 5. Yes. However, when we introduce this concept of branching effort, that's when we get fan out in multiple paths.
Do you not consider like each inverter, like 90 over 15, like should it be an H3 as well? Because like an H1 we took it to.
Right. So H2 is just here, right? So we have 90 over 15. So now we're trying to calculate 90 over 15, 15 over 15. So now we're talking about this node, and now we're dealing with this node as well, right? So we had calculated this previous path, now we're worrying about this other one. And we're accounting for that difference in this definition I'm about to present here, which is branching effort. And so we define branching effort. I'm going to scroll up just a little bit so you can see it. Branching effort is defined as the ratio of the total capacitance seen by a stage to the capacitance on the path. So we have the capacitance seen by the stage compared to the capacitance on the path. So we differentiated between the path we're worried about and the capacitance at that stage. You see how the timing, we have our input, so we have our output from this inverter, and we're driving both of these inverters. So we go on the path, and we have our capacitance off the path.
And why is that one path compared to the other one? It's the same thing, right?
Well, in this particular example, yes.
So the critical circuit is the one that well, that line not called.
Mm-hmm.
Yeah.
And this is where another challenge comes into play. The reason why knowing this is important is because let's say you've designed a cell, right? And your cell is going to be part of a larger, you're trying to design an arithmetic logic unit. So you've designed an adder. And your adder is going to be driving a certain number of outputs. You have a sum, you have a carryout. Your carryout's driving the next cell. And you don't, if you're just designing this, you have to count in order to be able to know the proper delay. You have to know the proper delay by knowing the contents of the next cell it's driving. So the path that we have the critical path in our adder. Critical path is our carryout. But each cell along the path is also driving your sum outputs. Now the sum outputs, if you recall from your data path design, it can go back to your registers, store the register, or it can be used to go to data memory because we use the summation load word to store word operations to go to memory. So now you have to worry about driving that particular bus to the output. So that's what we're understanding this concept of branching effort, this path branching effort that we're going to be going over here in a second. So what ends up happening is students design a cell, and it tests the cell, it meets all the noise margins, it meets all of my performance metrics, and then you put two cells together that you properly design, you expect them to work, but then they don't because they haven't accounted for branching effort. And so path branching effort is just the product of the branching efforts between stages. And so we're going to calculate our path effort delay, our path parasitic delay, and then we're going to calculate our total path delay by adding our effort delay and our path parasitic delay. And so I'm going to scroll up a little bit. Everyone's got 3.19. I want you to get it. Okay. So 3.21, the best stage effort occurs when each stage bears the same effort. So this is an ideal. We've designed it perfectly. Work perfectly. So here, let's say our f of 1 to the n, where n is the number of stages. And so we're trying to figure out the best stage effort. So let's say our overall effort is 625, right? And we have 5 stages. What would our best stage effort be? I'm just kind of pulling up a random question. We've calculated our path delay, path effort delay as 625. And we have 5 stages. So this becomes 625 or 1 to 5, which is just 5. So ideally, you're trying to break it down so that each stage has the same effort.
It's like matching impedances.
Yes. Exactly right. Matching impedances. The reason I'll go over this next TJ, but I think I see the formulation of the question. Maybe this will help. So now we're trying to figure out, we have our best stage effort. So we have our DOE, we figured out what our best stage effort, we got everything down to the same delay. Because you have different delays, you have your certain parts of the circuit have to work significantly harder to drive other forces into the circuit. So 3.22, I'm going to read it here, but I'm going to scroll up so you can write it down. The minimum delay of an n-stage path is the delay times the number of stages plus times our best stage effort. So if n, number of stages, times f to the 1 over n, plus the parasitic delay of the circuit. I'm talking about the path. Okay. And we scroll up just a little bit so you can see that. So the whole idea is that we have now calculated this best stage effort. We know our path effort delay. We know our path parasitic delay. So we know the full path delay. Based on that path delay, we know the number of stages. We try to calculate our best stage effort. And then best stage effort based on this, we can then go, well, we know the number of stages, we know our best case scenario, and we know the parasitic delay. Therefore, we can calculate the minimum delay of an end stage path, given the design. Now, to make it more complicated in section 4, where we go into power consumption, as we know, the dynamic power is directly related to the frequency. Sometimes you're going to find there's trade-offs between frequency and power consumption. So what you can do is you can try to minimize the full delay of the path. However, you have your higher frequency, you don't want that causing, you don't want consuming more power.
How do you equalize or harmonize those frequency meters?
We're going to go into that once in section 4.
That's what I'm talking about.
Yeah. I believe that at the moment, but that's a whole research field. And so we're going to go into an example here to kind of make this all try to make sense.
That was some of the optic circuits you're trying to put in play.
Yes. I wanted to read this as an excerpt from the textbook that I think is very important. This will help you be better engineers. So this is a key result of logical effort. This equation here, this minimum stage delay, it shows that the minimum delay of the path can be estimated knowing only the number of stages, path effort, and parasitic delays without needing to assign transistor sizes. So before you get into the whole idea of transistor sizes, which we did earlier in the section, you can calculate the minimum delay of the circuit. This is superior to simulation in which delay depends on sizes, and you never achieve certainty that the sizes selected are those that offer minimum delay. So if you're designing let's say you're designing a thermometer and it can meet a certain performance metric. So you have an 8-input binary from a sensor that sends the temperature. So it comes in, you need to be able to store it in a register, and you want to have a, let's say, Celsius to Fahrenheit converter, and you want to have some test beds in the circuit as well, so you can test to make sure the circuit is still working properly. You have to worry about the logical effort from the full path. You have to be able to store everything in registers. You can have a minimum and maximum. So you have your minimum value stored in your registers. You have a comparator. You have a maximum registers. You have your Fahrenheit to Celsius converter, and you have your control signals that you're controlling throughout the whole data path. So you have to worry about all of these when designing your circuit. So if you do all these calculations beforehand, and you figure out what the circuit should be, then you just put the cells together in the correct manner, make sure they're properly sized to that specification, and then put it in. And it'll save you weeks of design time. And sticking to this principle, when I took this course at the University of South Florida, the group that I was in, we still hold the record for the smallest design ever presented. And the reason why is because we actually did what we were taught in class, instead of just sitting there and fiddling with it, being frustrated, wanting to, go get drunk or whatever, right? That's what happened. So these are the proper design principles. Hey, let's work on everything. Let's worry about pathological effort. Let's worry about, minimizing the design. Let's worry about laying everything out first before we get into any kind of simulation. So that's a good fundamental to have. And that's why, for those of you who come to my office, if you notice in the upper right corner of my whiteboard, what Kevin tell what the saying is in the upper right corner of my whiteboard.
Better is the enemy of good enough.
Better is the enemy of good enough. We worry about vengeance. All these things put together. Okay, but does it do what I asked you to do? No, it doesn't. Okay, we have all these special doodads and everything you've accomplished, but it doesn't. The customer's not happy. So worry about meeting all the bare minimum stuff first, and then once you do that, then add special meet the customer requirements first. So, all right. So I've done enough going on a spiel about how not to waste your time doing designs. Let's talk about how to actually calculate this. So to determine gate sizes, working backward, apply capacitance transformations to find input capacitances of each gate given the load it drives. And so the end of the TGO, so we have our effort, we have our logical effort and our electrical effort. C out over C in. So then C in just becomes that gate's output capacitance over the total path effort, just by kind of doing some simple division. So now we have an example question here to show, to show what's going on here. Let me read this again. I want to make sure I'm clear. So we're working backward to apply the capacitance. So if we're working backward, we have the output capacitance here. Apply capacitance transformations to find the input capacitance of each gate given the load that it drives. So we're going to start with example 3.10. Let me read out the problem. Estimate the minimum delay of the path from A to B in the figure to the left. So in this case, the figure we have at the output, we have capacitance of 45. We have a 2-input NOR gate, but the fan out is to another 2-input NOR gate with a capacitance of 45. This node is the output of a 3-input NAND gate, but that is also driven by it drives two other NAND gates which are doing some sort of other logic, right? And that's all driven by a 2-input NAND gate with an input capacitance of 8. So the path is from A to B. Choose the transistor sizes to achieve this delay. The initial NAND 2 gate may present a load with 8 lambda of transistor width on the input, and the output load is equivalent to 45 lambda of transistor width on the output. Next, determine the gate sizes X and Y. So the first step is we're going to calculate our logical effort. We have our 2-input NOR gate. From our equation, we know it's 2n plus 1, so it's 2n, so it becomes 5. We also know that logical effort is the ratio between the capacitance and the capacitance of a inverter. So it's 5 over 3. We have our 3-input NAND gate. So it's n plus 3. So it's 5 over 3 again. And then a 2-input NAND gate. So it becomes 4 over 3. N plus 2 over 3. So you multiply that out, and that becomes 100 over 27. 25 times 4 is 100. 3 times 3 times 3 is 27. Next, we calculate our electrical effort. So it becomes 45 over y times y over x. So it's 45 over y times y over x times x over 8. So it becomes 45 over 8. I'm going to scroll up a little bit and see people trying to crack their necks a little bit here. So our branching effort, does everybody have 3.23? Okay. Branching effort, we have, you can either say 2 times 3 or 3 times 2, depending on how you're working forwards or backwards. This branches out and drives 3 gates. This branches out and drives 2 gates. So it's 3 times 2. So it becomes 6. That's how I got the branching effort. That's the multiple. So we start here. This is driving 1, 2, 3, right? Then on this path, it's driving 1, 2. So now it's 3 times 2. So now by doing this branching effort, we are now accounting for the branching for the path effort. So the path effort, it becomes the logical effort times the electrical effort times the branching effort. So we have 100 over 27 times 45 over 8 times 6. So when you do that out, you can tell this problem's been designed for simplicity because it comes out to a nice little simple 125. And then determining the best stage effort, we have 3 stages, 125 to 1 over 3. That becomes 5. So now we've calculated our best stage effort. So the next thing we want to do is we want to calculate our parasitic delay using that table that we derived earlier. 2 input NOR gate, 3 input AND gate, 2 input AND gate, 2 plus 3 plus 2, 2 plus 3, I'm sorry, 2 for the 2 input NOR gate, 3 for the 3 input AND gate, and 2 for the 2 input AND gate. So it becomes 2 plus 3 plus 2, and it becomes 7. Right? So we now have calculated our parasitic delay of the path. So now what we're going to be doing is we're going to be taking our best stage effort, our parasitic delay, and the number of stages to find our minimum, it's got to be estimate the minimum delay of the path from A to B. So in order to do this, we have to figure out the number of stages. We start from B, we have 1, 2, 3. So this becomes our minimum path stage delay, which is 5, we figured out. Times the number of stages, which is 3. That's 3 times 5 is 15. And then we've calculated the parasitic delay is 7. So it's going to be 15 plus 7, which is going to be 22. So here, using our equation, we've determined that, again, here's our, so we have F, it's going to be 1 over N. I've put in 1 over 3 already because we know the 3 stages. N is 3, 1, 2, 3. 5 we've calculated here for best stage effort. And then plus 7 is the parasitic delay. Sorry. Okay. So it comes out to 22. So now, since we know our best stage effort, and we know the output capacitances, values 5 over 3, right, for the logical effort, times the output capacitance, we can now go back and figure out our lambdas. So here, for Y, we have 45, right? We know that the logical effort is 5/3, right? For this 2 input NOR gate. And we know the output capacitance is 45. So using this equation that we derived from the TGO before, we have G, 5/3, output capacitance, C out 45, divided by our best stage effort. So we use this best stage effort to figure out the lambdas at each individual stage. Here, just becomes 45 times 5 over 3 divided by 5. It comes out to 15 lambda for this NOR gate. So that's how you can use this path effort to derive your lambdas. And then you use the lambda-based design rules that we learned in section 1 to actually design the NOR gate. So you can design the specific NOR gate here, as a 15 lambda, to work perfectly for this path effort for this circuit.
Where's the 15 come from?
Just it. You mean the solution? Okay, so I'm going to scroll up here to this equation, right? So we know our effort, logical effort times path effort, and we know that we defined this path effort previously as the ratio of the output capacitance to the input capacitance. So rearranging the capacitance to solve, rearranging the solve for the input capacitance, logical effort, best stage effort, times the output capacitance. So here we had 5 over 3. We knew that the output is 45, and we calculated our best stage effort is 5. So placing that into the equation, we then got this. And then doing the same thing for x. This is why we want to work backwards, because now we've calculated 15 here. So then we know our path delay is 5 again. It works out perfectly. I'm going to scroll up just a little bit so those of you in the back. We know that for the 3-input NAND gate, which is here, the logical effort is again 5 over 3, because n plus 2 for n being the number of inputs. So it becomes 15, which is what we calculated previously, times 5/3 divided by our best stage effort, which is 5. So that comes out to 10. So then our final circuit design, we have, using this path, we have all three NAND gates. Use those to calculate our lambda of 10. Both NOR gates should have a lambda of 15. 15 times 50 would be 5. Yeah, why is that 10? No, it should be 5. Yeah, should be 5. You're correct. That's 5. So. There we go. Now it's updated. Okay, so next we have up to this point we have some sort of design, and we're able to calculate the lambdas using some sort of output capacitance and some sort of input capacitance. And then we were able to derive this best stage effort based on the previous number of stages. So now we're going to go over an example where the number of stages may be different, and how the difference of the number of stages to calculate the same logical output and impacts overall circuit design. And this last example we're going to be going over with a 6-input AND gate will illustrate this very well. So given a specific circuit topology, so these are different circuit topologies. So we have some sort of inverter driving control unit signals. And here we chose a capacitance of 64 because it's driving a 64-bit data path. We now know how to estimate delay and choose gate sizes. However, there are many different topologies that implement a particular logic function. Logical effort tells us that NANDs are better than NOR gates, and we are able to figure this out because n plus 2 over 3, and then we have 2n plus 1 over 3. So if you plot those out on the graph, for example, we have 1, it's going to be 3 over 3, that's going to be 3 over 3. If it's 2, it becomes 4, 3 versus 5 over 3. So what's going to happen is 3 over 3, so it's going to be 1 and 1. So then NANDs are going to go like this, and NORs are going to go like that. So we want to use NAND gates as much as possible. So here, we're going to work kind of an example here where we're going to compare here we have one stage inverter, we have 2 stages of inverters, 3 inverter stages, and 4 inverter stages. So this example, a control unit generates a signal from a unit-sized inverter. The signal must drive unit-sized loads in each bit slice of a 64-bit data path. The designer can add inverters to buffer the signal to drive the large load. Assuming polarity of the signal does not matter, and that's why the important part of that statement is Here, it just inverts and goes to the end. Here, it maintains a similar. Here, it inverts because it has 3 inverters. Here it has 4 inverters. So assuming the polarity doesn't matter, which is rare, but just for the sake of the question, we will assume that. What is the best number of inverters to add, and what delay can be achieved? For that number of inverters, determine the transistor size. So we have 4 different stages of inverters, and we're going to be calculating for, we're going to do our same path calculation. We're going to calculate our best stage effort, and then we're going to use that to determine what's the best number of stages. And then based on that number of stages, we're going to calculate the lambda size. So to start out, for the solution, for one inverter, you just have one inverter driving a 64 capacitance. Our gate is 1. H is 64 over 1. F equals G times H, just 64. We know that our delay is going to be N times this square root. That's the same as 1 over N. So it's just going to be 1 divided by 1. So it's just 64 to the first power times 1 plus the parasitic delay of the inverter, which is also 1. So that just becomes 1 times 64 plus 1, which is 65. So that becomes our delay. For a 2-input inverter, we have the same thing. G equals 1. H is 64 over 1, just like before. Right? Because we can X over Y, Y over 1. So this becomes 2 of 64 square root plus 2, because each inverter has a parasitic delay of 1. So therefore, this becomes 8 times 2 is 16. Square root of 64 is 8. Plus 2 is 18. So now we come down here. Okay. For the 3-input inverter, same thing. G equals 1. H equals 64 for our output. G times H is 64. Our number of stages is 3. So it becomes 3 times the cubed root of 64 plus parasitic delay of 1, 2, 3. So this comes out to 12 plus 3 is equal to 5. Because 4 times 4 times 4 is 64. Plus 3 is 15. For 4 inverters, you're probably noticing the pattern. 4 times the 4th root is 64 plus 4. So this becomes 11.3 plus 4 is 15.3. So you can see we actually reach a point where it's going down, and then it comes back up a little bit. Therefore, based on this, we can conclude that the 3-stage inverter has the smallest delay. So, common mistake. I just do one inverter. I think that's going to have the smallest delay. It doesn't. It also is going to impact your ability to get to noise margins, because it's going to impact the sizing of the transistors. So then what happens? Simulate and tweak, simulate and tweak. Why won't this inverter work? Well, you should probably have 2 more inverters. That'll help. Okay. There you go. Math. So, for gate sizes, we're going to calculate our logical effort. 1 times 1 times 1 is 1. Wow. Electrical effort becomes 61 over 1, 64 over 1, just like before. Our branching effort becomes 1 times 1 times 1, because the fan out is 1. It's just driving 1 inverter, right? So there's no fan out between these ones. It's just 1 times 1 times 1 until we come down to 1 again. So our best stage effort, we have 3. 64 times 1 here becomes 4. So for this inverter, in order to calculate the lambda, we know that our output is 64. We know the logical effort of the inverter is 1. And we know that 4 is the best stage effort. becomes 4. So it becomes 64 divided by 4, which is 16. Now, that becomes the output of the third inverter. So going back up to our design, that's the size of this inverter here. That I'm okay. You can't see it because the screen's gone out. The one that's immediately next to the capacitor. So now we take that 16 value and do the same thing to calculate the size of the second inverter. We now take 16 times 1 over 4 because we know our best stage delay. 16 times 1 because the parasitic delay of the inverter is 1. The logical output is 1, which is 3 over 3. And divide by 4, so it becomes 16 over 4, which is 4. And then the third inverter just becomes 4 times 4 times 1 over 4, which should be 1. So now so you take lambda of 16, lambda 4, lambda of 1, do 3 inverters. If we were to do this here, right, if we had the best path delay for 1 over there, right, if we have 1 stage, that just becomes 64 over 1. So you have to make this giant inverter with 64 lambda, or you can have 3 smaller inverters, 16 lambda, 4 lambda, 1 lambda. So that becomes 20 lambda total. So you've now cut down the area by the size of 34, and it goes faster. Less area, less power consumption, works faster, better circuit. So hopefully this is why everything we've covered so far in this section is important. So as you can kind of see, based on these solutions, that you can actually have a point where you're going to, bottom out, and then just adding more delays to the circuit's going to have a negative impact. So it's an optimization type problem. So this next example here, and this is going to be the end of the section. So this problem here, your take-home exam that I'm going to be distributing on Blackboard on Thursday, ends here. It is currently 12:01, so we'll just spend the last little lecture covering this, and then on Thursday, here's how this is going to work. Make sure you do your TGOs, but you're not going to submit them, because I want you to have them for when you're doing the take-home exam. You will submit both the take-home exam and those topical guide objectives together on Tuesday. Do not do the material that we'll be covering on Thursday. I want you to focus on the exam material. Also, for those groups that haven't selected a project, get that to me by Thursday, because I'm accounting for snow issues. So does anybody have any questions about that? I'll go over it again once I distribute the take-home exam. So this particular example here, we have 4 different designs of a 6-input AND gate. So our first design is a 6-input NAND gate that we invert. The second design is 2 3-input NAND gates that drive. Now here, this is an interesting portion. I want you to combine concepts. We have an AND gate with 2 inverters on the input. So it's not A and not B. Here we have 3 2-input NAND gates and 1 3-input AND gate with the inverters. Likewise, we have 3 NAND gate inverter, NAND gate inverter. So now we have 4 stages, 3 stages, 2 stages, and 2 stages. So the first thing I want you to remember is, remember De Morgan's law, right? So not A and not B becomes nor A and B. So instead of having to have an inverter here, and an OR gate and another inverter, just reduce this down to an OR gate. So that's the first stage. So for the first design, what you're going to do is you recall, your logical effort is n plus 2 over 3. Well, it's 6 inputs, so that becomes 8 over 3. Our parasitic delay, we know it's n. So it's 6 plus 1 is 7. Number of stages is 2. So then taking our equation, we know n's number of stages, square root of a over 3 times h plus 7. And then, so we get this equation. Now, let me read the last portion of the problem. First, determine the minimum delay for the path for each design as a function of the electrical effort. Next, determine the minimum delay for h equals 5, 1, 5, and 20. This means we're driving a number of circuits, a number of stages where we have a fan out 4, h equals 4. We had some sort of theoretical h. The previous problem we had a 3-input NAND gate driving n 3-input NAND gates. That's h. So the way I'm setting up this problem is I'm initially leaving this value of h as a function. So for each design, I'm designing down to this function, and then what we're going to do is we're going to plug in the values of 1, 5, and 20. So a over 3, which we calculated the electrical effort, times h, which we're leaving undefined for the moment, plus 7, our parasitic delay, becomes, and I've done some reducing, but this is sufficient. Both on this problem and the exam, you'll be permitted to use Wolfram alpha to plug in these equations that you derived. I'm going to scroll down really quick to show you what I did. I plugged these into Wolfram alpha and got these particular slopes. And based on these equations, you can see initially one of them's better, but eventually this one becomes better. So you're trying to figure out what point here. So initially we get to 1 and 5, you get certain values, and then you get to 20, you get another value entirely. So for B, we have our initial 3 plus 2, 3-input NAND gate. So we switch this to an NOR gate, so it becomes 2 times 2 because it's 2 inputs, plus 1 over 3. So it becomes 5 over 3 times 5 over 3 is 25 over 9. Parasitic delay becomes 3 plus 2 using our table. N is also 2, number of stages. Therefore, the delay becomes 2 times the square root of 25 over 9 times h plus 5, which is our parasitic delay. We calculated 5 there, and I've reduced it a little bit. For this stage, we have 3 2-input NAND gates and a 3-input NOR gate. So 2 plus 2 to calculate the NAND gates over 3 times 2 times 3, 3-input NOR gate plus 1, 2n plus 1 over 3. So this becomes 4 over 3 times 7 over 3, which becomes 28 over 9. Again, because we have a 2-input NAND gate is 2, 3-input NOR gate is 3, so it becomes 2 plus 3. It happens to work out the same, it's 5. And then the number of stages again is 2. Plugging into the equation, we have 28 over 9 times h. 2 is the number of stages. This is also n square root plus 5 out the outside, and this is our reduced equation. And then for the fourth stage, we have 4 stages, but we have a 3-input NAND gate, so this becomes 3 plus 2 over 3 times 1, which is an inverter, so that's 3 over 3, plus, now we're using NAND gates again, 2 plus 2 over 3 times 1 because we have yet another inverter. So this becomes 5 over 3 times 1 times 4 over 3 times 1, which becomes 20 over 9. So here we've already gained benefit here by using NAND gates instead of including NOR gates. Our parasitic delay, however, becomes 3 plus 1 plus 2 plus 1. So that becomes 7. So that's where the trade-off is. Number of stages is 4. So delay becomes 4 times the 4th root of 20 over 9 times h plus the parasitic delay, which is 7. Now, I've taken the liberty of substituting these values for you for 1, 5, and 20 for each equation. For A, the initial equation is 10.3. For h equals 1, described with 5, it becomes 14 plus 3 and 21 plus 6. initially they're going to be all going up. So initially, 8.3 for B is lower than 10.3. This green and what? There you go. Becomes 12.5 and then 19.9 as H becomes 20. For C, 8.5 is less than 8.3. 12.9 is going to be less than 12.5. And then 20.8 is less than 19.9. Here for D, which is our 4-stage, we have 11.8 is very high if it's driving one bit slice. 14.3, it ties A now. So it was below A, and now it's tied with A, but it's still below B and C, right? Now we get up to H equals 20, and now we're down to 17.3. So for 1 and 5, we can logically conclude that design B is best. So for H is 1 as H is 5, this design is best. However, for 20, this design is best. So if we're actually using this if we're going all the way back up to this previous example here, where we're driving a 64-bit data path, we'd absolutely want to use D. But if we're only using it to drive smaller cells, we'd want B as the design. And this chart here is a description of where this is the point here between 10 and 11 where D becomes the most beneficial. Before that, B is always best, but here between 10 and 11, now it becomes D. So you would say anything from 1 to 10, design B is our best design choice, and from 11 on, D is our best design choice. And this Wolfram alpha, you can plug in all the equations, you can type them out, and it works out for you. And so, wow, that's a big example. Okay, we got 5 minutes. I can get through this. All right, so the number of stages affects the logical effort of the device. And so this is kind of a good combining concepts type question. The memory designer of the Motorola 68W86 is an embedded word automotive processor. The decoder is a 16-word register filled with a 32-bit word line. Each address is used to compute half of the 16 word lines, and each bit presents a load of 3 unit size transistors. They are given a complementary address of A is 3 to 0, and this becomes important because this is 4 bits. Each input may drive up to 10 unit size transistors. Targeting a best stage effort of 4, determine the best number of stages for the device. So by using what we know here, we have 3 unit size transistors and a 32-bit word line. Each bit presents a load of 3 unit size transistors. So we use that to do 32 times 3, which is 96. Additionally, each input may drive up to 10 unit size transistors. So that becomes 96 divided by 10. So let me read this out. The output load of a word line, 32 bits with 3 units of capacitance, or 96 units. Since each unit may drive up to 10 transistors, the path electrical effort becomes 96 over 10, which is 9.6. Since each address is used to compute half of the 16 word lines, this just becomes your branching effort becomes 16 over 2, which is 8. Splits them in half. So we're going to kind of neglect logical effort here because we haven't really, the problem doesn't indicate specifically what's going on there. But you can assume it's some sort of inverter, which is fine for this particular problem. So then our effort becomes G, logical effort, times the branching effort, times the electrical effort. So we calculate 9.6 times 8 times the logical effort, which we've assumed to be 1, and it becomes 76.8. Next, fourth root, we could determine the best stage effort. We find that n is equal to 3.1 approximately by using this natural log. and then we can say it's 3.1 is the best number of stages. So that's just kind of taking an industry example and plugging it in. This will be the last, this is the end of the chapter, but I do want to show you, here's an example of 3-stage design that actually does this. So 96 units of word line capacitance, it splits them up for, we have 0, 1, 2, 3, A equals 4, all the way down, right? So A0, A0 bar, A1, A1 bar, A2, A2 bar, A3, A3 bar. You see they both go into these NAND gates. They drive an inverter. So word 0 through word 15 just becomes their 16 bits. So we have 1, 2, 3 stages. And so we're able to calculate that logical output report. So we will start. I wanted you to do all the rest of chapter 3 for the homework assignment. And for those of you, about half of you turned in the Verilog assignment, chapters 3 through 5 from last week. Unless you've also turned it in there, you can have that done. You should have that done on Thursday as well. We will start next class with a brief exam review. And then we will start getting into power consumption. Does anybody have any? We got 1 minute. So,
One question.
yeah, sure.
Can you scroll through it?
Mm-hmm.
It says that 3 units of capacitance. Where'd you get that from?
That's from the problem. 3 unit size transistors. Yeah.
I was looking
Mm-hmm.
for it.
No, that's fine. That's why I wanted to include this problem, because I can throw all the logical effort and all that stuff, but I think this is a good problem for you to understand how these definitions that we're applying in this section apply to an industry type issue. So I see I have a 32-bit word line, 16 word register file. I also know that each line can drive 3 unit size transistors. I also know that each input may drive up to 10 unit size transistors, but each bit presents a load of 3 unit size. So based on the best stage effort 4, we can then determine the number of stages of this driver circuit. And last thing I'll say before I dismiss you, best stage effort is very important, especially since this is an automotive processor. If you put this type of processor in an embedded system that's actually kind of monitoring how cars are coming towards your car, let's say this is used to deploy an airbag. Use delay, that's what you want, right? Power consumption, I have an engine that's burning gasoline, I can figure out ways to get power, make it fast. Right? All right, so in that case, everybody is dismissed. If you came in late, please turn in your homework.